a concept from theoretical physics that is, frankly, pretty mind-bending. We're talking about the Unruh Effect. It's a prediction from quantum mechanics that completely overturns, well, what we thought we knew about empty space. It even challenges the very definition of a particle.
Yeah, it's definitely one of those ideas that sounds almost like science fiction. But it comes directly, straight out of the fundamental principles of quantum field theory and relativity.
Right. And we're not just, speculating off the top of our heads here. We're digging into the source material for this dive, specifically excerpts from an analysis called the Unruh Effect and the Observer-Dependent Vacuum.
That title alone kind of gives the game away, doesn't it?
Yeah.
Observer-dependent. It's all about perspective.
Exactly. So our mission today is to unpack this bizarre phenomenon, try to grasp its truly wild implications, and maybe figure out why, despite being so important theoretically, most people haven't really heard of it. It's a journey, really, into the heart of quantum reality relativity. And it all seems to depend on how you're moving.
Okay, yeah, let's get into it. Starting with that idea of empty space. What does that even mean?
Right. So classically, intuitively, you think of a vacuum as, nothing, yeah. Just emptiness. A void.
That's the picture most of us have. You suck all the air out of a box, and what's left? Empty space. Simple.
But modern physics, specifically quantum field theory, QFT, it tells us something radically different.
Oh, completely different.
The vacuum isn't empty at all.
Not even close. According to QFT, the vacuum is actually the lowest energy state of the ground state of fundamental fields that fill all of space-time. It's dynamic. It's not static. People sometimes call it a seething environment or teeming with latent energy.
Like a restless ocean, maybe? Even when it looks calm on the surface, there's stuff going on underneath.
Exactly. And this is where we get concepts like quantum foam or those fleeting virtual particles that are always popping into and out of existence. They don't stick around, but they're sort of a sign of this underlying energy.
Okay, got it. So the Unruh effect takes this quantum vacuum idea and then adds motion into the mix.
Precisely. And it makes this really startling prediction. An observer who is accelerating through this quantum vacuum, they won't perceive it as empty. They'll actually perceive it as a warm bath of thermal radiation. Basically, they see particles.
A warm bath. Just because they're accelerating. But hang on, if I'm just sitting still or maybe moving at a constant speed, like cruising along in the exact same spot, I see nothing, just the normal cold vacuum.
That's the core of it. That's the really radical implication. An inertial observer, someone moving at constant velocity, sees a perfect zero-temperature vacuum right there. But the accelerating observer in the same place at the same time detects heat, detects particles.
Wow. So the very idea of what a particle is, it's not absolute. It actually depends on how you're moving.
It really seems to suggest that. It means that concepts like nothingness or emptiness, and even what counts as a particle, well, they might not be universal truths. They might depend entirely on the observer's state of motion, their frame of reference.
Okay, this is really messing with my head a bit. So how? How does just accelerating turn empty space into a particle party? You mentioned particles aren't tiny balls, but like excitations in fields.
Yeah, exactly. In QFT, like we said, the universe is filled with these fundamental fields, electron field, electromagnetic field, you name it. And particles, things like electrons or photons, they're just localized excitations. Think of them like ripples or vibrations on these underlying fields.
Okay, so a particle detector is basically looking for these ripples, these excitations.
Pretty much, yeah. So an inertial observer, let's say you, sitting still, you define the vacuum as the lowest possible energy state of these fields, zero ripples. Your detector registers a particle only when it sees an excitation above that ground state. Seems straightforward.
But the accelerating observer, their view is different.
Completely different. Because their frame of reference is constantly changing. Special relativity tells us that changing motion warps your perception of space and time. And this constant change forces the accelerating observer to use a different mathematical language, you could say, a different set of basis modes to describe the quantum fields around them.
Different math, okay. How does that suddenly create particles out of nowhere?
Well, here's the crucial bit. What the inertial observer correctly sees as that single lowest energy state, the pure vacuum, the accelerating observer's math interprets differently. From their perspective, that same state looks like a mixture of states. And critically, some of the states in that mix include excitations.
Okay. So their detector, which is calibrated to their accelerating frame and their definition of vacuum and particle, it picks up these excitations that are part of the mix.
Exactly. And this is a key point from the source material. For the accelerating observer, these are not virtual particles. To them, they're real, they're detectable, they form a thermal bath. The vacuum state, as they define it from their accelerated perspective, genuinely contains these thermal particles.
Wow. So the definition of the vacuum and even how many particles you count,
Yeah.
it becomes observer dependent.
Dependent on your motion. That's
Yeah.
a huge shift.
It really is. And it leads to the next question, right? If the accelerating observer sees these particles, this thermal bath,
Yeah.
how warm is it? Is there like a specific temperature?
There is, and there's actually a formula for it, isn't there? The Unruh temperature.
That's right. The temperature, usually written T subscript U, is given by the formula tens on 10, 2 sub A.
Okay, that looks maybe a bit intimidating, just a bunch of symbols.
Right.
But they represent fundamental constants and that key factor, acceleration. You've got R, the reduced Planck constant, that's from quantum mechanics. You've got RE, which is the observer's acceleration. That's the motion part.
C, the speed of light, hello, relativity. And K sub, the Boltzmann constant, which connects energy and temperature, that's thermodynamics.
And this formula, this is where it gets really profound, because it directly links a purely kinematic thing, acceleration, just how your motion is changing, with a thermodynamic thing, temperature. It just beautifully weaves together relativity, quantum mechanics, and thermodynamics, all in one prediction.
It's almost like finding out that, I don't know, how fast you tap your foot somehow changes the air temperature around you in a predictable way. But, you know, on this incredibly fundamental cosmic quantum level.
That's a fun way to think about it.
Yeah.
And what's also fascinating is that this whole mathematical structure, it doesn't just live here. It pops up somewhere else, somewhere perhaps a bit more famous.
Ah, right. You're talking about the connection to black holes.
Yeah.
To Hawking radiation.
The bridge between the Unruh effect and Hawking radiation is Einstein's equivalence principle, which basically states that being in a uniform gravitational field feels exactly the same locally as being in a uniformly accelerating reference frame out in space.
Okay, so standing here on Earth, feeling gravity pull me down. That's physically indistinguishable in my little local patch from being in a rocket ship accelerating upwards at, what, 9.8 meters per second squared?
Locally, yes. The laws of physics work the same way in both scenarios, according to the principle. So now think about an observer who's trying to hover just outside a black hole's event horizon. To stay put, to avoid falling in, what do they have to do?
They have to fire their rockets like crazy, right? Constantly accelerating away from the black hole just to stay in one place relative to it?
Precisely. They're constantly accelerating in a very strong gravitational field.
Okay, and the equivalence principle says that strong gravity is like acceleration.
Right. So applying that principle, the experience of that observer hovering near the black hole is, locally, the same as the observer accelerating through empty flat space, the one experiencing the Unruh effect.
And what does the Unruh observer see?
A thermal bath of particles.
Ah, so the observer hovering near the black hole must also see thermal radiation.
Exactly. And that thermal radiation, seen by the observer near the black hole, that is Hawking radiation. So the Unruh effect provides this really crucial theoretical underpinning, almost an independent verification for the physics behind Hawking radiation.
Yeah.
The math is essentially the same. It grounds Hawking radiation in these broader principles of quantum fields in accelerating frames.
Okay, that makes sense. It connects it all. So if this effect is so theoretically important and it supports black hole physics and it links up these huge areas of physics, why isn't it more famous? Why haven't we, built an Unruh detector and just seen it, measured that temperature?
Yeah, that's the paradox, isn't it? The simple answer is the sheer, almost unbelievable amount of acceleration required to get a temperature that we could actually measure.
How much are we talking?
Okay, get this. To produce an Unruh temperature of just 1 Kelvin, and remember 1 Kelvin is incredibly cold, just 1 degree above absolute zero, the acceleration needed is calculated to be about 2.4 times 10 to the power of 22 meters per second squared.
2.4 times 10 to the 22,
It's huge. To give you some perspective, Earth's gravity is about 9.8 meters agations. This acceleration is roughly 2.5 quadrillion times stronger than the gravity you feel right now.
2.5 quadrillion Gs. Okay, yeah, that's a lot.
It's an acceleration that is just completely, utterly beyond anything we can currently engineer. No spacecraft, no centrifuge, nothing we can build can sustain anything even remotely close to that kind of uniform acceleration.
What about particle accelerators? They get particles going incredibly fast, right? Huge energies.
They do, but it's generally circular acceleration. And while related effects might occur, The clean, classic Unruh Effect prediction is for uniform linear acceleration. It's just a different physical scenario, and the required linear A is the challenge.
I see. So there are ideas for how we might detect it, like proposals involving intense lasers or special electron storage rings.
Oh yes, absolutely. Physicists are clever. There are theoretical proposals on the table,
Yeah.
but they all face just enormous technical hurdles. The signals predicted by these experiments are incredibly faint. Trying to pick them out from all the background noise would be, well, extremely difficult. It's theoretically possible, maybe, someday, but practically, yeah, very, very tough.
So, okay, even without that direct smoking gun experiment, the Unruh effect still stands as this really important pillar in theoretical physics.
Absolutely. Its significance isn't really diminished by the experimental difficulty. It fundamentally redefines how we think about the vacuum. It shows us it's not just this static, empty void, it's a dynamic thing, and its perceived properties like temperature, like particle content, they depend entirely on how the observer is moving.
And it really challenges our basic concept of what a particle even is. The number of particles you count isn't some absolute fact of the universe.
Exactly.
Yeah.
Plus, as we saw, it elegantly ties together relativity, quantum mechanics, and thermodynamics,
Yeah.
showing just how deeply connected they are.
Yeah.
And of course, it provides that vital theoretical support for our understanding of black holes, particularly Hawking radiation.
Right. So the core takeaway here seems to be that the reality an observer perceives, it's fundamentally linked to their state of motion through space-time. What looks like empty space to you or me might actually be a warm bath of particles if you just looked at it while accelerating like crazy.
That seemingly empty void holds this hidden thermal energy, yeah. Just waiting for an observer with enough acceleration to kind of reveal it.
Okay, well that I think wraps up our deep dive into the Unruh effect for today. We've seen how just accelerating through what we think of as empty space might actually feel like swimming in a warm particle soup. It really challenges our fundamental notions of what's real, what's empty, what's a particle.
Mm-hmm. It definitely highlights how space, time, motion, and these quantum fields, they're all far more deeply tangled together than our everyday intuition tells us.
Yeah, this isn't just abstract physics, is it? It touches on the very nature of perception, of reality itself at the deepest level, and it leaves you with maybe a slightly unsettling, provocative thought. The Unruh effect tells us that some really fundamental truths about our universe, like the energy hidden away in empty space, or the fact that particles aren't quite as solid as we think. They only really show themselves under the most extreme conditions, conditions we can't even create yet. So what other incredible secrets might the universe be hiding, just waiting for us to find the right perspective, or maybe the right acceleration to finally see them?